we're going to start with the next part of the lecture, which is on textures. Originally, this lecture was actually meant for next week, and we were going to do lighting this week. But I felt like the burden of lighting is pretty high. There's a lot of calculations and a good bit of math necessary to get it to work. And since you're all just starting to learn what shaders are, why not spend a little bit more time with shaders and do something very easy, which is manipulate textures. And then next week, after you have 2 weeks of shaders under your belt, you'll be able to slip into lighting a little bit easier. So that's kind of why I flip-flop things on you. Let's go to 10. So we need to begin by loosely understanding why we have a need for textures at all. So to begin with, we know we have vertices. We've already discovered this in the last several assignments, right? We've created vertices, and we know that we can also assign color to vertices, and the graduate students had an assignment where they needed to add color for the vertices. However, if you think about this, and that was the only thing you could do, which is add colors per vertex, well, that's fine. I could put a vertex here and here and here and here. But the issue is that colors are interpolated between them, right? So if I specify one shade of red here and a different, like a darker shade of red here, and then maybe a more of a brown color here and an orange here, it linearly interpolates the color values between each one. So you end up with this gradient across the different corners, and it will be smoothly interpolated unless you disable interpolation, which is an option. Just keep that in the back of your head. However, if you're creating a complicated surface, such as a brick wall we see here in this back, it would take thousands and thousands of points, and then you manipulating the colors of each of these points in order to create something that even began to look like this. And actually, this is a big problem because we do get data sets like this. If you have ever experienced laser scans or any kind of scanning equipment, you know that they will take thousands, if not millions, of collected data points, samples, and some systems will also sample the color information of the scene and place that color per vertex. Some will also do textures, as we'll learn, but for the most part, they're also sampling and placing it per vertex. So you now have millions of points, which might accurately recreate that object. However, you have millions of points describing possibly just a single brick or maybe multiple bricks on a surface of a face. How are you expected to get that thing to run in real time, right? If you're trying to do an entire scene. So if you're doing an entire city block, right, or Grand Theft Auto or whatever you want to, that's going to have millions of bricks, right? This will not work for you. So what we need to do is to think of some way to make this actually work. And not only that, but even the macroscopic details, right? The microscopic details, the tiny holes and pits and the little bits of lighting that go across the surface, all of that would need to be ingrained within the vertex data. And now you're looking at tremendously complicated objects that don't really give you much information whatsoever, really aren't that important. So what we need to do is we need to figure out a better way of handling the situation. And conveniently, well, we all have cameras, we all have, cell phones that take pictures of just about everything. Wouldn't it be nice if we could take that picture data and use that on the surface as opposed to needing to use additional polygons? The idea being that we could then optimize the geometry to just represent the macroscopic shape of the object. That is the large shape of the object. So a brick maybe could only be a few polygons, or you can see here with this particular brick here, I put a few different vertices here and here, and I went ahead and extruded it out. So it's got a little bit of the same shape as before. But the image that we provided, the picture that we took, would provide all of the meso details. Meso meaning middle level details, all the color information and the blotches and the irregularities that the bricks would actually have. However, there is one other layer, and we're not going to talk about that next, and we're not going to talk about that now. That's next, and that's the microscopic. And microscopic details usually impact the lighting of the object. That is how it looks, whether or not a surface is plastic or shiny or metallic. Typically, those are the microscopic features on the surface that we then see or presented to us when the light shines off of it, interacts with that object, gets diffused or reflected perfectly, and then enters our eyes. So there's a different level for each of these. The macroscopic is the geometry itself, the large geometry details. The mesoscopic is going to be our texture. And then the microscopic would then be our lighting model, how our object reacts, or how we program it to hopefully react to light. So the next question is, all right, so we've got images. Let's just say we've done this, right? We've got all these images. We've got a collection, a database of stuff. Well, what really is an image? And if you take digital image processing next semester, that's offered, you'll learn a lot more about this. You'll learn about different formats, and I can only cover so much here. So I recommend, if this is an interesting topic to you, that you jump on board and take it. But loosely, an image is just an array. Some faculty will describe it as a vector, a one-dimensional vector, and you specify a width and a height, and that tells you when to start the next column. Others will call it a matrix of information because it's two-dimensional. It's up to you. I usually just call it an array of information, usually a two-dimensional array. The resolution of an image is determined, of course, by the width and the height of the element, right? And then images are usually 2D. However, they can be 1D, although even 1D isn't really 1D. It's not like it's infinitely thin. It is a single pixel wide, but of course, whatever height you want. In this case, this is a gradient that was used in our Picatinny project to visualize the different damage levels, where we had two different levels. We had the low damage levels, which were these, softer pastel colors, and then the high level damages would roll over using pretty much the same colors, but then at a greater intensity or a higher saturation. But you're not done with just 2D or 1D textures for that matter. In fact, you can have three-dimensional textures, volumes of information, and these would come from CT scanners or other scanning systems where you have entire volumes of data, usually from medical or even from civil engineering applications. So you can use several of the different scanning techniques that are available to them to load that data in and to visualize the earth, the ground, all sorts of different things. Or you could use data run from a simulation in fluid mechanics and then overlay that and then view it as volume information. And then if you want to, you can even do 4D or time varying data. Now, of course, with each one of these, the size of the data set, well, grows very quickly. It grows dimensionally, right? For a 4D time varying data set, even a small amount of data at a relatively normal resolution, like 1024 by 1024, will get big very quickly. So here's two examples over here. Of course, we have an 8x8 grid of pixels. 8x8, of course, makes for 64 total. And then we have down here an interesting one where it's a three-dimensional texture that is actually generated procedurally. That is, an algorithm is used to determine what values to place on the surface. So it's not a cube of data, right? Instead, it procedurally, for each of the pixels on its surface, evaluates a function, and it provides to that function the three-dimensional coordinate of each of these pixels. And then it determines what the value should actually be, in this case, based on a marble function that would approximate how marble flows through the object, probably using some sort of randomization algorithm and so forth, and some interesting artifacts here. Then, of course, there's image depth. And depth is incredibly important. We mentioned it before in a prior lecture, but that's what is actually stored within each of these pixel elements. And not only does the image size determine, the size, how big an image is going to be, the container you need to hold it, but in many ways, it's the depth that really causes an image to balloon in size. And if you can use a smaller depth, or you can use a smaller container for each of the pixels, then the entire thing will get much smaller, much more quickly. Now, images images in general to the layperson are described using megapixels or gigapixels, where you simply multiply the width by the height. And for me, at least, that's a horrible way of explaining how good an image is, because technically you could have a 1 by like 10 million pixel. And what good is that other than maybe scanning documents, right? To me, you need a little bit more information than just a blanket pixel number. So here's an example of four-dimensional varying data that I created several years ago. This was an interesting project. Let me see, how do I get to just a pointer, please? Just a pointer. There we go. So here, we'll go ahead and play. And this is a beating heart, a real person's heart. We received some cardio ablation data from a company, and they were interested in using my volume rendering algorithm to see the heart beating in real time so they could determine whether or not there's something wrong or whatnot. And basically, it's multiple volumes of three-dimensional data. And we're cycling through them with this slider you see up here to visualize what's going on. And you can imagine if you played that back at a normal frame rate, you would then, of course, see it beating. The reason it's so blurry, you ever try taking a picture of a heart, let alone a picture of a person trying to stay still in a CT machine and having their heart beating? It's not easy. Usually the scanning system has to be synced up to their heartbeat, but you can't exactly cause a person's heartbeat to be regular. Every tiny stimulus that's around them, their breathing impacts where their heart is and how it beats. So it's very difficult to get non-blurry, high-resolution data for something like this. Okay, so we talked about an image and we got an idea about that. And then I talked about depth and how that's really the pixel value. So what is a pixel? Well, a pixel stands for picture element. And yeah, whoops. That's the name makes a lot of sense. It's an element within a picture itself. And there can be many different formats based upon the range of data you can capture. And we only talk about a few here, but I've been to a few conferences a long time ago where people were working with bit depths that were obscene, hundreds of bits for each individual pixel. And they captured large ranges of the electromagnetic spectrum. And these were mainly for military application. But you can imagine you just keep increasing the bits, capture more data, more information, and you get more to show, so to speak. So pixels can vary in format. A pixel itself is within the array. And here's some different ones that you'll commonly see, of course, 0 or 1, black or white, or it doesn't have to be black or white. It could be any color you decide to associate with it. If it's an old school Fallout-esque monitor, it might be black and some weird green color, for instance. Then you have gray, 8 bits, 0 to 255 values. And usually we think about that as more of a transparency type effect. You could also have integer values instead. You don't have to use that. And what integer values are used for is to look up a palette, a table of colors that you pre-generate that only have the colors pertinent to that particular image. So within the image itself, it would store a palette of the colors you want to use. And then each of the pixels would store maybe a value between 0 and 128 or 0 and 256, looking up a specific color. So images that would have large ranges of color with a palette system wouldn't look very good. However, if you have images that tend to be within a specific quadrant or area of the color sphere or the color circle, you would actually be able to approximate how that looked pretty well with a palette. And if you ever want to see really good palette stuff, just go back and play any of the old adventure games like, not Commander, was it Commander Keen? I can't remember, but I think Space something or other, I forget what they were called, but all of those were typically done with palettes by a company called Sierra at the time. And the artists did some amazing work with palettes. In addition, you could always use different techniques to, similar to a newspaper, blend different palette colors together to create a third color, where every other pixel would be one color and then the other pixel would be a different color. And then if you get enough of them together, it would start to kind of look like a different color on your screen. Then we have R5, G6, B5. I mentioned that one before. The idea being that green is the most important color. That's the most sensitive color for most human beings. And then you get 65,000 colors out of that. Then if we go ahead and do 565 and then 1 for the alpha, actually, this is incorrect. This should be 555 and then 1 because usually you keep your size stuck to a bit or a byte. You stick to bytes because those are the smallest containers of memory that you're usually able to access through most programming languages. Therefore, this doesn't make any sense. 5, 6, 5, 1, because then you would have one more than you would the number of bytes, right? Because this would be 6, 5, and 5, so that would be 16. So that would be 2 bytes, right? 8 and 8. This would be 17, makes no sense. So that's, once again, apply logic to what you see, and it should make sense. So this way I know that I screwed up. This should be 555, and then that one extra bit you took from the green is being used as a binary on and off mask for the transparency of the object. And then we have the common convention these days, 8888, which gives you 16 million colors plus 256 different transparency values. And then these are some images I found on Wikipedia. What you need to understand about these images is that they are using an adaptive palette. Like I mentioned before, that's why they look somewhat good. If you were to take these images into Photoshop and then reduce the bit depth down by hand, these would look pretty nasty. It's only by using a palette of colors that you're able to actually get something that looks like the original image. So formats. I want to talk about formats for a second, just so you're familiar with what you should or shouldn't use inside of Unity. Technically, Unity supports a lot of formats. In fact, maybe too many formats in some cases. But each format has a different structure to it, code. You can look up most formats online, unless they have some sort of a patent or a license or whatnot, in which case you might not be able to. But things like the BMP or the standard bitmap has no patents. It's a really easy format, and actually has many features that most of you probably don't know it even supports. Usually when you make a bitmap, you go into like old school paint on Windows and you would just draw something out. Move my chair out of the way. But the idea is that a BMP file can actually have multiple bit depths. It actually supports compression, which is something that most people don't know. It can even have alpha and color profiles, but those are usually more advanced features. A typical bitmap is uncompressed and will support a standard bit depth that you're familiar with of either a palette or usually the 8, 8, and 8, and have no transparency at all, and of course no compression, which is why if you zip a bunch of bitmaps, it gets so small because none of the data is actually compressed within the file itself. It has the ability to be compressed. Then we have, of course, GIF or GIF, which is a hilarious thing if you've never looked into the pronunciation problems with it. The developers of GIF or GIF pronounced it as GIF. And the reason why they did this is because they came up with this horrible slogan, choosy developers choose GIF, from the peanut butter brand. However, in 2020, Smuckers made fun of this by releasing these different jars where they kind of set in stone, or they didn't, but you know, the joke is that it's now set in stone that GIF is for peanut butter and GIF is for images. So even the peanut butter makers are kind of on the side of the public on that one. But GIF is interesting. It's only an 8-bit pixel color format commonly, and it uses an internal palette, which is why they can look pretty nasty from time to time. It's compressed, and it of course also supports animation, although we as a people are now moving away from that and using movie files instead that are far better at compression. Then we have JPEG, and JPEG is going to be a file format that if you do jump into the digital image processing course that Shriek teaches, you'll learn a lot about, because it uses the discrete cosine transform to actually compress the image down. And you'll learn about how you can increase or decrease the level of compression by how many of the DCTs you decide to sample, right? Because each of those are a wave, right? So if we go to screen pointer, and you do your DCT, your discrete thing, and you get different values. And the idea being the highest frequency information will be over here, and it'll be really, really big. And then you determine through the algorithm at some point where you want your cutoff to be. And you remove all the higher frequency information and only preserve the lower frequency part of the spectrum. And then you undo that to get the image back. And that's one of the homework assignments you'll have to do, or labs you'll have to do in this class if you decide to take it. It's kind of interesting. The problem with JPEG is natively it doesn't support transparency. In addition, it's lossy. You lose the results. So while a photographer, and by the way, if you ever have a wedding or any kind of major event where you have a photographer working with you, one of the things you should try to ask them is to get the original raw data and not the JPEG data, because this will always be, unless they know what they're doing and they turn off or they turn compression up to the minimum. You will get a lower quality photo. In addition, if you're given the raw format, typically most photographers' cameras will store data in 10 or 12 or even 16 bits per pixel, as opposed to the lower quality ones we were talking about before. 16 per channel. So red would be each of these, green, blue, and so forth. And what you're able to do is modify the dynamic range of the image, so you can change things if the brightness or the darkness of the image was too much or too intense. It's very easy to take that into a program and manipulate those, because your monitor can only show 8. So you have to choose the range. So if this was all the values that your camera has, right? These 8 bits, you choose the range that you're able to see, or you extend it over the entire range, but you start losing pieces of it. They get averaged together. So that's why I would recommend, if you can, talk to your photographer about getting the raw data if you want to have the ability to manipulate and edit that data and have it as it was originally captured. And if your photographer tells you that they were only shooting in JPEG, they're full of it, and they don't want to give you the originals. PNG. Portable network graphics. This is my preferred format to work in. It's all over the web. It supports transparency, and more importantly is it has compression, but it's lossless. So you're not going to lose any image quality by keeping something as a PNG. Now, that being said, there are PSD files, Photoshop files, okay? What you'll learn is that Unity will accept them. And the power of a Photoshop file is the fact that it supports multiple layers, all right? So you could have part of the image here, 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 and here, and you can go back, manipulate it, edit it, do whatever you want to. I don't recommend working with them natively within Unity just because they're large. Unity has to convert them over and flatten them, and that's what you'll end up using inside of Unity. Keep the files separate if you can. So let's go ahead and move on. Okay, so now we've talked about that. Let's actually discuss textures then. So we know what images are, we know what pixels are, we're all good with that stuff. So what is a texture? Well, texture is just an image, okay? Nothing more to it than that. And what we're planning on doing here is we're going to map this image, as we call it, a texture information, to the surface of the triangle. So an object, here's a demogorgon I made last week. Remember how I said I was like overwhelmed? Well, one thing I didn't mention was that it was my son's 8th birthday party. And since we have to do everything remotely, I, a day beforehand, decided to create an entire Roblox level for him and his entire class to join so that they could all have a party together in the same place. And of course, he wanted unique assets. So one of those was a demigorgon model you see here. So I made this very quickly for him. But the idea here is that each of these different objects is composed of triangles. For the most part, it's composed of quads, as you hear, because quads are actually easier to work with topologically. The algorithms inside of 3D modeling programs like quads. It's easier to understand. When you have a triangle like this, right? Moving from one side to the next is actually not easy. When you have a quad, though, it's easy to differentiate the parts. This is the left side, this is the right side, this is the upside, this is the downside, right? That seam in the middle really can mess things up in certain algorithms. So you'll see most people model with quads, and then what they do is they'll export it out by having the program triangulate it. So then all these will then become triangles at the end of the day. And that's something you actually have to be careful of, and you'll learn about that later when we get into Substance Painter and other things. But the idea is that for each of these vertices on the object, you now need to specify an additional vertex attribute. So what have we looked at so far? We looked at color, right? And we looked at normals. Now we're also looking at adding what are called UVs to each one of these vertices, okay? An image, regardless of the size. So I don't care if you give me a 1x1 image or a million by a million image. In terms of computer graphics, this is always 0 to 1, okay? That is 0, 0 in the lower left-hand corner to 1, 1 in the upper right-hand corner. We normalize almost everything in computer graphics because it becomes so much easier to work with, right? You never know what the size of an image might be. Think about it. If you're the designer of Unity, right? You have no concept of what the size of an image is. You also might not know what platforms you're going to be working with in the future, right? An Android cell phone has different hardware than my PC in front of me here. It can handle different sizes of textures. I can fit maybe, 128 by 128 textures on my cell phone, but I could maybe fit the same number, but at 4096 by 4096 resolution. If I was using the resolution to store information, I'd have to change that based upon whatever platform I'm developing with or whatever size of an image I happen to be working with. That's a horrible way to work. So usually everything gets normalized to a range of 0 and 1, regardless of the size. And the reason for this is because it's easy to take that 0 to 1 range, multiply it by the width of your image to calculate any pixel value, right? So 0's here, 1's here, you give me the size of your image, say your image size is 1024. Well, if I say my value is what, 0.5, all I do is I multiply 0.5 by whatever the size of the image is, and I get the exact pixel, 512, that I want at this particular location to work with. So that's why everything is between 0 and 1 as many times as possible, because they're easy to then scale up or scale down or manipulate however we see fit. So, okay, we've got this. So we've got 0, 0, 0 down, or 0, 0 down here, and of course, 1, 1 up here in the upper corner. The coordinate system is usually called UVW. Do not believe any of the BS people will tell you that UV stands for something. It doesn't. It stands for absolutely nothing, just like X, Y, and Z doesn't stand for anything. It's just another set of letters in the alphabet other than X, Y, Z. Because XYZ is already commonly used for position data, they didn't want to confuse people. So they use a different set, which is UVW, usually just UV, but like I said, it could be three-dimensional. So you might have a W coordinate in there. Another optional one you might see from time to time is STW as well. Don't worry too much about that one. You might see it in some older documentation. For the most part, we've moved on to just saying UVW for texture coordinates. Another nomenclature thing is many times you might see people referring to them as pixels. This is, once again, to try to separate all these different things that are going on, right? So we've got pixels on the screen, we've got pixels in the texture, we've got fragments going on in between. So we try to give things different names. So we usually call the individual pixels within the texture we're dealing with the texel values, all right? So those are the individual values inside of that image, not the pixel value that gets evaluated and drawn to your screen. So you also see that very commonly. Okay. The process from moving from the 3D surface of, say, a triangle or something else for that matter, to the 2D surface is not trivial. And there are a lot of things you need to consider. I'm not trying to scare anyone once again, but the topic can get a little bit deep, and it does take experience to know what's right and what's wrong. So here are some questions. Should every triangle on my entire object be split apart and laid out individually onto this two-dimensional surface? This example you see here is just that. I literally took every single triangle. Luckily, these are algorithms. That means I only have to click a single button. I didn't actually have to grab every single face and do this manually, but it laid them all out throughout the entire thing. The great news is that the algorithm looks at the plane and determines, okay, how should I place this on the surface to maximize surface area? It's as flat as it ever can be. And since all triangles are planar to begin with, that's a definition of a triangle. If these were triangles instead of quads, everything there would be perfectly laid out with no distortion. Why do I bring up distortion? Because if you try to unwrap an object, right, you'll always end up with some sort of distortion. If you try to take an object from three-dimensional space to two-dimensional space, and it is a truly three-dimensional object, and it lives in that space and uses all of the coordinates, when you bring it to 2D, you're going to lose data. It's the curse of dimensionality. I don't think Polakar teaches machine learning anymore, but that used to be a big thing in his courses, was that when you're dealing with machine learning, the curse of dimensionality, as you add additional data, things become more complicated. And what you usually have to do is you try to reduce the dimensionality of that by finding things like the eigenvalues and the eigenvectors, right? So what I'm trying to say here is there's no perfect solution. I mean, technically this up here is as close as you'll get to a perfect solution. But the problem is it's a giant mess. It is what we would call a triangle soup, literally. If you had a bowl here, these would all be floating on top of it. It's a mess. In addition, there's problems with different algorithms that we'll find out later when doing it this way. However, so what's a better idea? Should the surface be continuous? Should we try to keep it together? The idea being that we can readily identify the different parts of the Demogorgon right here, right? So this is probably the center, the back of the head. Oh, actually, this is the back of the head. This is the mouth. These are the different leaves that come off. You have a sense of what this is. And since it's a two-dimensional image that we're talking about, you're probably going to have an artist in Photoshop or a similar program, and they need to be able to draw on this thing. Could you imagine drawing on this thing up here? It'd be a nightmare. How do I even know which? They're all at random orientations. Everything's a mess. Here, at least, things are laid out in 90-degree angles, and we can kind of get an idea. And you could always write like, oh, this is the face, or this is the upper right part of it, so forth. So it makes more sense. However, what you'll notice here is that I've colorized these. And what I've done here is shown you the amount of distortion present by keeping them together. These were curved surfaces, or somewhat curved surfaces beforehand. If you ever try to take anything curved for that matter and flatten it down, what happens? It'll split or it breaks or it warps, right? It distorts. Stresses and strains build up. And that's what you can think of these colorations showing you, is where the maximum amount of distortion is. The redder the part of it, the more it's been distorted to fit into that location. And you can do things like add cuts to the different parts of the surface to try to relax the object and let it, sort of fan out or slip out from its area, and that'll reduce distortion. But with every cut you add, it becomes harder to paint on the surface of, right? So here, on this surface here, I can take a paintbrush and literally just draw straight across it, right? It doesn't matter that I go from one polygon to another. just draw right across it. And as someone making that object, I understand it. Up here, if this is one polygon and it happens to be connected to this polygon over here, how the heck are you going to draw a straight line? I start here and go to here, but the orientations don't even match up. So maybe this line going this way now for this object would actually need to go over and to the left or something. As you can see, this might be optimal. This might be the best way to not have any distortion, but it's a horrible way to work. And that's why we typically keep things this way. There is a caveat to this, and you'll learn it when we get to Substance Painter, because no longer do you need to mess with the 2D image itself. You can now paint directly onto the 3D surface if you have a GPU powerful enough to do it. And that will help you out a lot so that you can get away with nasty meshes like you see up here. And you're starting, I'm starting to see these nasty UVs, as you see up here, a lot more often, especially in YouTube videos by people who are self-taught, who don't want to take the time to lay things out correctly. So I just want you to know you will begin to see this more often, things kind of abstracted and ripped apart more, because the software is compensating, is allowing them to do that. One last thing I want to mention here is if you're sharing vertices, once again, but I need unique texture coordinates for two triangles. For instance, if we look at the, let's clear this out again. So come here, I need to learn the hotkeys. If we come down here, this vertex here, and let's say this one right here are the same. They share the same point in space, right? However, because I've split these up, they need separate texture coordinates because they're in two different locations. Therefore, I need to define one vertex for this location and another vertex for the other locations. And as I had mentioned earlier, this is where people get into problems because they will have made this split here, right? But they won't realize that that split means two separate vertices exist. Therefore, things like seams, hard edges might become apparent later on because they've split stuff up. So just keep that in mind that when you're splitting up a UV, you're actually splitting the vertex. Because the vertex is the fundamental atom for computer graphics, for every vertex you specify, you can also attach additional attribute data, right? So if you want to have different attributes at this location, you would then need to have separate vertices at that location as well. And that's where optimization becomes a big problem. And you can read more about that or look it up on your own if you want to. But the idea that what you export this model as might not be the exact size that you end up on the other end. So you might export from your 3D modeling application an object that's 100 triangles, right? But based upon these splits that you add, when it gets to the 3D engine, the engine might have to interpret and break things up. And then you might end up with 200, 400, or even more. And things bloat in size. And the next thing you know, you've completely destroyed your polygon budget. So just keep that in the back of your head.
Quick question, George.
Now we need to talk about the texturing pipeline. Alex, did you have a question?
Yeah, is there a situation where, for example, if you needed hyper detail, where you might want to use the tessellated triangles in the top example? Or is the value of having everything grouped together, even if distorted, heavily outweigh that level of detail that you get?
So I hesitate to answer your question because it actually requires more in-depth knowledge. And some of those topics we will touch on tonight. However, there are many times when the texture you're using does not line up with the polygons on the screen. For instance, you'll notice that many of these are at odd angles, right? And what is an image? An image is a set of squares, right? That's what it is. But if you have a line that crosses over these squares like this, right? Well, what's it going to be? What color value do you use? What happens if you have two different versions here? Here, you're kind of right here, but you're really close to that edge. Should you be sampling this or should you be sampling a blending of all these? So what you'll end up with is what's called aliasing artifacts, these stair-step jaggies that go through your surface. So breaking it up this way, you're going to have this aliasing problem on literally every single polygon of your entire object, which is going to be very bad. Let me put it that. It's going to cause all kinds of visual artifacts. In addition, another thing we're going to learn about are bitmaps, where you take the image, say you have a 1024 by 1024 image. Bitmaps make smaller versions of that at different resolutions so that when you're sampling something from very far away, say say you have a pixel right here on the screen, right? But you have an entire city that's sitting there way off in a distance, but it's all within that single pixel, right? How do you know what color to make that when an entire city sits there? You can't evaluate the entire city. So this is where you'll get into different stochastic algorithms that NVIDIA and AMD like to tout about how their graphics cards determine what they're going to do. So they might take multiple samples or random samples, or they might use AI to do some sort of weird sampling on this thing as well to make it more intuitive. But the idea being that is if you have different texture sizes, right? If you take an image that is let's say I make a halfway mark through it or something. This is pure black and this is pure white. And I have this image down, right? What usually happens is that the pixels right here get averaged together. So you end up with values you never anticipated. You now end up with gray values on that seam. Take it down a size smaller. You end up with additional values, maybe 0.075 over here, 0.5 in the middle, and 0.075 over here. Each time you downgrade that image, usually some sort of averaging filter is used, which causes you to get new values. In addition, if you've ever averaged values together, which we all have, right? 1 plus 1 equals 1, right? And then you divide it by 2 or whatever to get your final color value. When you average things together, you only get dimmer, darker, so to speak, right? As you begin averaging all these pixels together, the intensity of the image is going to darken as well. Most of these problems are automatically taken care of now. They've been solved by hardware and different algorithms, but these are the kinds of things you have to fight with. And because you have different resolutions of these images, what happens when you get to the really tiny ones, right? Like 128 by 128. Obviously, 128 by 128 pixel map here, you might have several of these polygons all sampling from the same region. So now all of a sudden, what you thought was a nice texture with lots of details all over the place for each of those areas, now you only have one pixel for all of these to sample from. So all those parts of the object are now being averaged together with the surrounding parts of it, which cause issues as well. So it's a big topic, and there's a lot of problems, and there are solutions to it. But usually you want to try to keep some form and structure to your object to stay away from all these other issues. In addition, this allows you to have some redundancy, this allows you to not have redundancy on your vertices, right? So the only vertices on this object that need to be specified twice are these corner ones out on the side, because those ones will have two UVs. They'll have one specifying this area, and if this point and this point are the same vertex but different UVs, only the edge ones need to be duplicated twice to have two distinct locations in UV space. However, all the ones inside don't need that. This point here, even if it's 4 different points from the 4 triangles next to it, right? They can all be represented as one single vertex position and one single UV coordinate. So it keeps the size of your data set down as well. Okay, so those are all reasons. Here, this is an explosion of junk. This, on the other hand, is beneficial in several ways. However, there could be a case that maybe there's actually, if we calculated the area, there might be less area wasted here, whereas here you have large swaths of area that are actually wasted. So you can see there's pros and cons, but for the most part, we're going to kind of go with this one over here, where you've got some form and structure keeping things together for the human being, us, as well as for compression and several other reasons. Does that make sense?
Yeah, as I understand it, it sounds like it's not something that you can simply boil down to complexity versus usability. It's a lot more complicated than that, and you really have to choose how you're going to approach things for any given task. So,
Yes.
Yeah, that makes sense.
There is no right answer. It's what is your situation, and here are your choices. Pick the one that works best for what you're doing. This I consider lazy, and you'll see this a lot with new people. This is not lazy, takes a little bit more know-how, but in the long run is usually better for everyone.
Got it.
Okay. Now we need to talk about the texture pipeline. So this pipeline is important. This is something you should commit to memory. This is something that might show up on a midterm, for instance. At least generally understand what each of these stages does. Because if you can figure out what the stage, if you understand the pipeline, you can figure out what the names mean. And the names make sense for the most part. The entire process of a 3D model, looking up a texture coordinate, that is, we go from 3D space to the two-dimensional image, right, the grid, and figure out what that is, follows this pipeline that you see here. We start with the vertex itself in three-dimensional space, right, an XYZ coordinate. And what we're going to do is we use a function. Now, we call it a function, but the reality is most of the time this is done, it's not real-time evaluated. You use some sort of a function or method to project it to two-dimensional space, and you store it away as a vertex attribute, as a UV position that's stored within it, and you don't recalculate it ever again. However, we call it a projector function because very often you can use, especially in procedurally generated content, an algorithm in real time to determine how to go from 3D space to two-dimensional space. Obviously, there's no real algorithm from going from the Demigorgon head to this layout you see in this lower area right here. This is me using several different functions on different pieces to convert them over, okay? It's a process that I went through. So it would be, if this was to be done in real time, this whole thing would be maybe 40 different function calls to make it happen, so to speak. So what we're trying to do is, if you remember, the vertex that comes into the pipeline is in what's called object or model space. That is the space that it was designed in by the artist or yourself if you're doing it by code, right? And many times you put it at a convenient location, like the origin. So if you're making a triangle for a homework assignment, you probably put either one of the corners or maybe the top or the center at 0, 0, 0, right? But in reality, you want the triangle somewhere else, right? You're not making everything at the origin. You are building a world, so you need to transform them. And a matrix is used that transforms it by translate, rotate, and scale to the appropriate place. So what we're doing is we're taking the object space coordinate, although it doesn't have to be object space, but that's usually how it's said, and you are mapping it to another coordinate system, which is usually called parameter space. That's your UV coordinate system. And that process is called mapping. Usually, all this is done pre-computed within a 3D program and you store it away. And actually, I can open up an object file if you want to, and we can look at the raw ASCII characters, and I can show you how this is laid out in one of these file formats if we have time. But the idea is you can calculate these values in real time or pseudo real time. And many of the procedurally generated games you see today do that when they generate entire worlds. These are the steps down here, each of these, right? So right now we're on the projector function step. We are going from object space here, and we're ending up in parameter space here by the end of it. So some projector functions. When we get into using Blender, or if you have a preferred modeling program, so long as it's not like SketchUp or something really basic like that block one for Minecraft, you will have projector functions. And this is actually a snapshot of the last version of Blender that I used. I think it's 2.82, and the different UV projector or projection, as they call it, functions available to you. And the common ones you have are planar, which means that it comes at it from a plane. So it'll take your three-dimensional object, let's say we have a person's face, right? And depending upon which plane you select, whether it's Z, X, or Y, it will flatten that object. So in the case of a face, if you come at it from the Z direction, it will look at you like this. If you come at it from the X or the side, your face will look like this, right? You'll have a face and then a smile to the side. If you come at it from the top, you would then maybe see a little bit of eyes here. And if it had hair, you'd see hair from the top. Those are the projections. It's taking your three-dimensional coordinates and flattening it down into two-dimensional space. We'll learn more about this when we get into the actual doing inside of Blender. You have camera, which instead of being a specific world coordinate system, we'll use your camera instead. So if I have a camera right here, right, and it's looking arbitrarily at some location in the scene, say right here, and here's my angry guy. He's not happy. And I project from this direction, what'll happen is it'll come from this direction. So what I'll end up with is something coming at it from the side. Maybe I'll see it from right there, a little bit of the eye right there, maybe a little bit of the mouth, but mainly the back of the head because that's where it's pointing. It allows for arbitrary orientations. When you're new to things, people stick to like planar, cylindrical, or spherical, or even automatic. When you get better, I almost always just use camera because I never use any of these other types to do anything. Camera does it all for me, and I use some other techniques, which I'll talk about in a second, called seams to do the rest of the work. Cylindrical is for when you have a as it says, most of these are for the object that's mentioned there. So what this will do, and I'm going to draw it for you because that makes it a lot more clear. For a cylinder, it assumes you have some sort of a cylindrical object like this, right? And it's got points and vertices and edges and so forth. And what it does is it takes the object, and you usually, let me get a different color. So that's my cylinder. What usually happens is it will give you something that looks like this, just like the cylinder, except it's see-through, and there'll be a line going down here. And this is the seam. This is where you want to make a cut down it. And what it does is it takes your geometry, adds the seam to it, and then tries to unroll the geometry. So what happens is you end up with a seam like this, right? And then slowly it'll unroll it until finally you're left with something flat like this, okay? And usually with a cylinder as well, it might do a planar projection on these top parts right here, because obviously this top is flat, and if you come at it with a planar projector straight down, that's the best way to unwrap that particular surface. So a cylinder might look something like this. You'll have flat here where it's unrolled, and then you'll have the top and the bottom right there where it's been planarly ripped off. And then we'll go and clear this off. So next up, spherical. Once again, it assumes you have a sphere, and with a sphere, we've got all these problems, right? If you ever look at a globe, you know you got problems with distortion, right? Because Antarctica and everything in the high north look like they're giant, and everything in the middle looks squashed together. And that's because of the projection used, the Mercator projection system. The only time you get minimal distortion is when you see those maps that are like this, right? Where they got those cuts in them, because the cuts have removed the distortion. The maps you see like this, what they've done is they've just said, all right, we're going to connect this point to this point and warp them together. So you stretch out the surface to be much larger than it actually is. So as you can see, UVs actually have basis in reality and everything. They're not just a computer graphics thing. It's a real problem whenever you're taking a three-dimensional object like the world and trying to flatten it onto your screen. So spherical will put a point at the top, a point at the bottom, give you a sphere, and then once again, just like cylinder, make a line where it's going to rip that thing apart. And what it tries to do is it tries to separate the object out like this, and sometimes it'll look like this where it'll have some jaggies on the edge. But either way, it's doing something very similar to cylinder, where it's making a cut along the object and trying to unfurl it or unwrap it. Actually, it'll probably end up looking more like this, okay? Where these are the points emanating out from the central position, and then you'll get more severe warping. Most of the time, what you'll end up doing for beginners is you'll actually take the sphere, you'll cut it into two halves, right? So you'll have this side right here, and you'll have the other side over here, and then you'll flatten it out into two halves instead to minimize distortion. And next up, we have automatic. Automatic sounds fancy, but usually what automatic means is you specify how many planes you want to come at this object. So if you specify 6, right, it will then come at it from up, down, left, right, forward, and back with a different plane, evaluate all the polygons, and whatever polygon comes back with the maximum surface area, that's probably the best plane to look. So you could do fewer or more. You could do 8 and do weird or dodecahedrons or crazy objects. But the idea is it's coming at it from multiple angles and it's trying to determine the best one to use. Now, what I'm going to promote in this class, and it's probably what everyone uses as soon as they get out of the novice phase, are seams and flattening. It depends on the program you're using. Some programs have seams. Blender does, but the idea is if you have if you have an object, let's say you have a bodybuilder's arm, right? Big muscle arm, right? It's got all these weird curves all over the place. This guy has been taking too many steroids. How do you cut this off, right? Well, we could try to use a cylinder here and here, but that's kind of a pain in the butt. Instead, what you do is you say, okay, this bodybuilder's arm, this bodybuilder usually has his arms down. And usually if he does have them up, you look at it, he's got his flex going on right here. And there's his bicep and so forth. But usually you never see the back part of the tricep. So what you do as an artist is you put the seams in places where you know the person's never going to see. Because this inside seam is never going to be seen for the most part when the arm is down, because it's snug against the side of this guy's body. And because when he raises it up, you never see that you'll never see this tricep part. What happens is you end up selecting the edges that go along this part, and you say, this is where I want to make a cut. This is where I want a seam to be. And then if you do it correctly, so that the seams begin and end at the same place. This entire big bulky arm ends up unwrapping to something that might look like this. Right, so this would be the top of the bicep. We'll put a vein in there so you know it's the top. There we go, big one. And here's a little bit of the elbow right there. But the idea is you're unwrapping it based upon seams that cuts that you put into the surface and rolling them out. And that's the exact same thing I did with the Demigorgon. I found convenient locations that I knew no one would notice. Why do I care about people noticing? Because regardless of how good you are or the applications you use, seams pop up. Errors, glitches, all kinds of things, they will appear. And when you have a seam, you'll have pixels that are different on one side than on the other side. And those immediately cause people to lose, well, faith in the fact that you know what you're doing. Most lay people won't notice them, but as soon as you learn a little bit about computer graphics, you'll see seams in every single game that you ever play. And usually there are automatic systems you use that will take the seams you've added and then try to stretch or flatten that object out in a way that minimizes distortion. And this is where you get more into the art of UV unwrapping. Where do you put the seams so that they are not noticeable? And where do you put them to minimize distortion? Okay, once again, last thing about projector functions is if you're still not understanding it, if you can't visualize it, I'm a very visual person, so this all makes sense to me, but if you can't, here's the closest approximation that I've come up with. And the idea is very similar to skinning an animal. Well, I'm not going to skin an animal for you in these lecture slides. I'm pretty sure I'd get into a lot of trouble for that. So instead, we're going to be skinning or unpeeling an orange. So an orange is a three-dimensional object, right? So we put a line down it, and then we decide to cut it open, and we remove the inside, and now we have this shell, this outside, right? That's our polygonal surface, and we want to flatten this. What happens as soon as you try to flatten an orange peel? Well, it starts breaking because an orange peel isn't rubber. Now, in the world of computer graphics, it wouldn't break. What would happen is it would distort, right? So what you would have is these parts still connected. But now, if you think about it, if an image was right here, this little bit right here, that is just maybe this part of the surface and this part of the surface, is stretched out over a much larger area. If it's stretched out over a much larger area, there's a lot more pixels in that little area than over here, for instance. The pixel density increases very high. And then you start noticing weirdness with the surface where there's more pixels in one area than another. If you ever play any video games, look at the pixel density on the 3D models. Now, if they're doing things right and it's a modern game, you won't notice this so much. But on a lot of the older ones, you'll see where they distorted or stretched things in order to give more pixels to one spot, like the face of a character. That's an important part. So they'll give more pixels to that as opposed to maybe the arm or shoulder or the back. Or, for instance, under the foot. How many times do you see the bottom of a character's foot? Almost never, right? So why would, that's a really bad foot. At least, come on, George, give it a shot. Something like that. There we go. I'm going to put some toes there. You never see this, right? So you would scale this down so that it only takes up a couple pixels on the UV map, and you can put the face, right, to be really huge, happy face, and make that better. So all I'm trying to show you here is that when you're trying to flatten an object, there's no right way of doing it. There are better ways and worse ways, but either way, you're going to have to deal with distortion and things breaking apart. Okay, the next part is the corresponder function, or functions as it's called. And this is a chance for you to transform the UV coordinates before you actually sample a pixel value. Why would you want to do this? Well, we're actually going to use a corresponder function at the end of the class where we're going to move the UVs so that it appears like a texture is moving. So you could do this with water or anything else for that matter, to scale things up or scale things down or have them flow throughout the entire object. The idea is that it gives you a chance to manipulate those points that might have been baked in by some artist on a 3D model and manipulate them however you want to. And by default, all the textures that you supply to Unity already actually have a corresponder function. If inside the inspector, when you attach a texture to a material that has an appropriate shader, you will not only have a slot for the texture, you'll also have two other fields. One of them is for tiling, and the other one's called offset. And we saw this in the last class where I was moving those sliders around and I made, I think it was a lava texture repeat several times. What's happening there is it's passing in a matrix to scale in or up that data or down that data. So it's manipulating the UVs that were made in the 3D modeling program by this transformation matrix to either, offset it either to the left or the right or up or down, or to have more or fewer of that texture on that surface. So Another really important thing, and I'm not going to talk about it here as much, we're going to talk about it when we get into Unity, is the wrap mode. The wrap mode is what happens when you exceed the 0 to 1 space. So I said that we go from 0, 0 in that lower left-hand corner to 1, 1 in that upper right-hand corner. But what happens when you go outside? The wrap mode that you dictate is going to specify what happens when you go outside of those coordinates, because many times you will want to have your object exceed the 0 to 1 space. For instance, let's say I have a ground, let's pick a different color because I have green on the screen. Let's clear this out and let's go to something else. Let's just do white. No, white is bad, isn't it? Let's do, I don't know, purple. So if we have a street going way off into the distance, right? And we made a texture over here, this is a texture, and this is our actual geometry. And let's say this geometry, I only used 4 vertices. I used it to make 2 triangles. And this is a huge street. Okay, there's a person here. His name's Bob. He's a construction worker. This is a construction simulation game. And we made a texture where we created maybe half the road, just a part of it. Here's the line right here, a yellow line. That would be yellow. And this would be asphalt, crackly asphalt over here. We want to use this texture on this surface. With wrap modes, we can have this one texture completely fill up this entire thing with an image. So if you didn't have a wrap mode, right, and you couldn't exceed 0 to 1, well, we could put 0 here and the maximums over here, and then you would have this large, the asphalt would look huge, right? Next to this little character right here, you'd see giant cracks all over the place, and you have a single line going down here where the median is of the road. With the proper wrap mode selected, like one called mirror, we could specify that this side in the X is 0, and this side over here in the X is actually 2. And with mirror mode, when we get to that seam where it crosses over between 0 and 1 to 2, so this would be 0, this would be 1, and this would be 2, it mirrors the texture over automatically. So what you would get is, on this side, the asphalt over here, and you get half that line. And then when it mirrors over to the other side, you get the other half of the line, and then you would get the rest of it.
I didn't even realize you could make the enum public. Oh well, already submitted it. I don't really give a shit. So.
Wow, Richard.
Yeah, I really don't.
Live to everyone.
Oh, my bad. I'm sorry.
All right. Well, for everyone out there, you can make enums public. And please do give a crap. That being said, so the idea is you can use this one texture. Why would you do this? Well, because you can store, you can use a smaller texture now that takes up less memory to cover an entire road surface. And not only that, you can use a single polygon with only 4 vertices to do an entire long road, right? Because if we also choose one of the wrap modes to be repeat on this edge up here, so mirrors on this side and we choose repeat, this could be so long that the texture would repeat multiple times and it would just be doing the same bit over and over and over again. So a very small texture, maybe 512 by 512, and a single 4 vertice object could be used to create something that would look, well, if you tried to do this manually, you would need to create multiple breaks in this object at each of these locations, separate vertices, throughout the entire object. Guessing people are on Discord or something. That's probably why things got mixed up. So that being said, we'll learn more about them shortly. Here's an example that I made of wrap modes. In this case, once again, where is the, I thought there used to be just a pointer object. Of course not. There we go. So this is one I did a long time ago where I'm manipulating the UV coordinates with a matrix. So it's moving the UVs through space as an offset. You'll notice the geometry doesn't move. However, it creates this natural twisting motion. So I didn't need to animate anything other than the texture itself, which was far easier to create this sort of surreal space that you see. This was actually used in a Doctor Who demo we created a long time ago. And I believe I used to have TARDISes flying around as well. Now, if you take that and I were to also rotate that surface maybe in the opposite direction, you could create some pretty psychedelic and interesting effects doing that. So I'm just trying to show you that there's interesting reasons for why you would do things. All right, that being said, let's move on to value determination. The corresponder function will have produces. Well, I need to double check myself, don't I? The idea here is that we need to convert these values. I said that they're typically between 0 and 1, right? So we need to convert a floating point value into an actual index into an array. So an image, if it's 128 by 128 pixels, right? That's a two-dimensional array. You need to convert that over into an integer value. So this process here, value determination, is taking that and converting it to an index value. So for instance, in this case, if we were sampling, let's say this is our image and we want to sample right here, that is 0.5, 0.5. The image is 128 by 128. 128 times 0.5 is what? 64. So now I know I can index into 64, 64 into my array to grab that value. But you might say, hey, George, if you're using a triangle, right, you're going to have lots of weird values because it's going to rasterize across this. And you're going to have to get values all the way across here. When you convert, that is when you multiply 128 by 0.51, you're not going to get an index value. So what the heck do we do? Well, usually what happens is it will look at the pixel that you're evaluating and see where it falls, okay? And then what we'll do is based upon where it falls, it will sample this pixel, this pixel, this pixel, and the nearest neighbors, and it will use a summed weight of them. So if this one is really close to the center, but it's on this pixel, this one will obviously get a larger weight. This one, less of a weight. So it might be, let's say, a factor of 2 here, 1, 1, and 1 over there. It'll all be based upon how far away it is from each of these other pixel center points, pretty much. And that's how you would average them together to determine values that are between pixels. This is a wonderful example. It comes from Real-Time Rendering Edition, and it has been known to be on midterms in the past. And what it is there's an eye and it's looking, and we're rendering to a screen right here, right? So imagine there's a screen with pixels. And what we're trying to do is figure out what this pixel value here is right on the screen. So we're sampling this location. We see the model, it's an object space. We convert this. So these are the XYZ position of object space for that pixel. It gets converted over to its UV parameter space, which happens to be 0.32, 0.39. So if we had a texture over here where this is 0, 0, and this is 1, 1 up here, right? So then we would go 0.32 over in the X, and then we would go 0.29 up in the Y. And we would end up somewhere around there. Obviously, this is not to scale. And next up, we would then convert that over to our image space texture. So we would need to know what the size of this was, but we multiply these values by whatever the width and the height of that image is. So let's just say it's 256 or something. We would end up with these pixel values you see here. And then we would index into that particular array within the image, and we would find this color value, okay? And that's what we would work with. The final, I say it's optional because many times it's not used, but you should be aware of it, is the value transform function. The way to keep this stuff in your head, I find, is, all right, I need to go from my 3D object to my 2D world. Then I need to be able to either manipulate if I'm outside of those values, or I get the chance to change those values before I decide to look it up, right? This is my chance to mess around. Then whatever value I've calculated, I get the pixel value. Now that I have the pixel value, before I decide to use it, I get a chance to mess around again, right? So here I get to mess around, both of these ones, and I can transform that value to be wherever I want to. So if I did get a texture value, I might, let's say I had all of my artists working so that all of my textures were evenly lit, right? The idea is that my game is for, they don't know yet. The art director can't make his mind up, or her mind up. They don't know what they're doing. And halfway through the game, they decide, well, everything's too bright and nice. Let's darken this. So they create a shader or a filter that operates on these textures afterwards. Or there could be things like gamma or other values of the texture that might be pre-processed or baked into it, and you need to change that value to get it to work on something else. This is where you would do it. After you find the pixel, now you can manipulate that value to be whatever you want to. Another great one is grayscale. Let's say you're doing some sort of detective noir game, right? You might have created the entire game in color, but let's say at the last minute, they decided to make certain cutscenes grayscale or a change to gray. If you've never looked it up, there's a really interesting formula. I forget what it's, something like 0.3 times the red channel, 0.5 times the green channel, like 0.2 times the blue channel. And each of these constants in front relate to how sensitive your eye is to different colors. And if you multiply all these together and then add them together, you end up, one, this is a value of 1, so that's kind of convenient. But 2, you end up with a single monochromatic value that has used the RGB values to be determined based upon your sensitivity of your eye. And now you can convert a color scene into a grayscale scene. Once again, another use for your value transform function. In the case of this charcoal shader that I showed off before that I had written a while ago, I use multiple texture lookups to determine what the value should be across the face. And I sample them together and interpolate across the surface to figure out what the final look should be for any of the particular characters. So here's another area where you might need to do something like that. All right, now's the time where we can finally talk about Unity and textures. These are the different file formats for textures. What I highly recommend in this course you use are PNG files, all right? PNG files, because they're not lossy, you won't lose anything, right? So if I tell you, oh, something looks bad, you can always go back and bring it up and manipulate it. JPEG, great for compression. However, many times Unity will compress your stuff for you based upon the platform you choose. So why not use PNG and let Unity do the compression later? If you're using Photoshop, it does accept PSD files, but just like all the different file formats it accepts Blender files, Maya files, 3D Studio Max files. I recommend not doing it just because if you remember when we talked about that artifacts folder, right? The artifacts folder is all the process data. It's got to take the PSD, which is multiple layers, flatten it down to a single object, all right? So the benefit of using a PSD is you only have one PSD file. It's in your Unity project. So if you manipulate it or edit it, Unity will then crunch it down to a single flat image and use it. The problem with it is you're also sharing very large assets with the rest of your team. So if you have a PSD file in there, PSD files can get massive if you have not used them before, gigabytes in size when you have lots of layers going on for large particular objects. So why would you want to share that with your entire team? Instead, take a few seconds and just export it out as a much smaller file format to work with. All right, HDR for high dynamic range ones, TIFF and Targa, you'll see in different locations. IFF is a Maya file format, if I remember correctly. The other thing that you need to understand is that POT, power of 2 is what it stands for. Textures need to be a power of 2. Now, the width and the height don't necessarily have to match. That is, you could have a power of 2 of 256 by 1024. The important thing is to have them as powers of 2. The reason for that, once again, is we're working with a computer. Everything's binary. Binary, we have bits. Bits are actually mainly bytes that we work with on a memory level. The smallest amount of memory we can typically access on a computer is usually a byte. We don't access bits. Instead, we access a byte. And then within a byte, we can then perform bit operations. But it's almost always a byte in size. Therefore, if you stick to a power of 2, the memory that is being used up by the texture fits perfectly into a power of 2 slot. That's why we do that, okay? If you do not use non-power of 2 or NPOT textures, most older hardware does not support them. And what happens is it takes your non-power of 2 and it will convert it to a power of 2, which means it will average pixels, distort your object, your image, and ultimately produce something that you might not want. In addition, if it's let's say it is 257 by 257, it doesn't downsize it to the nearest one. Instead, it will make it 512 by 512, right? So what you had was a 256 image, now taking up 4 times as much space because now it's been scaled up to a 512 by 512 image. So that's a great way of completely destroying your memory footprint there. So I recommend just stick to powers of 2. Unless the only time not to are for GUIs. Many times GUIs or sprites in 2-dimensional games, power of 2 doesn't make sense, or you might waste a lot of space with powers of 2, unless you do things like creating sprite atlases or texture atlases, which we can talk about at another time. But usually those are the only times non-powers of 2 are something you can work with. There are hardware limitations as well based on hardware. These are the different shader models. Remember, we talked about shader models before, and 2004 and before, that's what the minus means, the prefix of the minus. Before 2004, and with this version of OpenGL, ES is for mobile devices, okay? So whenever you see a GL ES, that's for a mobile. You have 2496, then we jumped up to 4096, 8192, and of course, 16,384. However, no one uses textures that big. So what you need to understand is that Unity has a maximum cap as of right now with 2019 of 8K textures. And you're not going to be doing 8K textures. I can tell you right now, especially not in Substance Painter. If you all were worried about using an integrated GPU, you will not be able to support 4K textures most likely. Usually you'll be using 2048s. You'll be manipulating them or smaller. Okay. In Unity, we have a texture. If you select a texture or if you select a material that supports textures, you will get a texture slot over here on the side, and you can drag and drop your texture into it. But before you do that, you actually need to get a texture in your project. And these are the different ways you can work with textures. You can either drag and drop it into your project folder from another folder. You can use the import command in Unity to import your file or multiple files. You can import a model file, usually an FBX file. And many times this will have both 3D model data embedded into it, as well as textures and material data. And when you select the FBX asset, there's some buttons in the inspector that say extract. And what you can do is extract the textures from the file and the materials from the file so that you can work with them or manipulate them however you see fit. You can also create textures through code. We're not going to talk about that right now. We will talk about that when we have our lecture on procedural content generation. So you can make textures yourself with your own algorithms. And then, of course, you can create textures through rendering. As we talked about before, you can do passes, right? And you can create what are called render targets so that the output of your shader goes to a texture, and then you can use that texture to then be used somewhere else, like a mirror, right? So imagine if you have a mirror on a wall, you might create a camera that's behind the mirror and that renders the entire scene from this object's perspective, right? And then you assign it to a texture, which is then assigned to that surface. Do you see? So you'd actually have multiple render passes. You'd have your camera over here, which is the person right over here looking at the scene. But before you do this, you would render this camera, store it to a texture, assign it to this object here. Then you would do your main scene render pass over here. And then you would render the mirror with the texture applied to it as if it was looking out at the rest of the world. That is one of the reasons why reflections, mirrors are usually ignored in most video games, even current cutting edge, latest gen ones, because doing it requires a second render pass, right? You just doubled potentially the how much you need to render in the scene to get this thing done. So that's why they'll usually have them smashed in, right? And broken, because they can kind of fake it if you don't have a real reflection. They can make this look a little blurry and nasty and not so good. Okay, so let's see. So yes, through the inspector, when you select a material, you have slots. After you load them in, you just drag and drop them. Or if you click and hit select, it'll give you a list of textures and you can choose them however you see fit there. You can also assign textures to material slots through code if you want to as well, by accessing the material through the mesh renderer if you want to, and then assigning one as you see fit. When you select a texture inside of Unity, you actually need to, you've got lots of different options. Once again, because the texture you have in the project is not the same texture that's used in Unity, right? You load a texture in, it gets processed based upon the settings that you put here, and then the artifact folder holds the final version based upon what you choose inside of this window. So the first option you have when you select the texture is its type. Usually this is left as default, but there are other kinds of textures out there, such as cube maps and so forth, that instead of being a two-dimensional texture are actually laid out two-dimensionally, but might be multiple views. So for instance, if this was a cube map, this might be the front, the top, the bottom, the left, the right, and the back side of it instead, all laid out like this, kind of like if you ever did origami with a box before, how you probably did in like grade school, and you can roll that up to make a box. This texture is storing data differently than the two-dimensional one over here. So that's why type would be important to change. Same thing with shape. Here's cube maps once again right there. That's another option you might be able to deal with. The sRGB one is a deceptive option that almost everyone gets wrong. Luckily, Unity automatically fixes this for you in most cases. However, sRGB was developed by Microsoft and HP in 1996, and it defines the color space. So you've seen those pictures. I put it up several times where you've got this color space, right? This weird looking triangle, and this is like green, red, and blue, or maybe flip the two over here. And then the color space is the triangle that can, these are the valid colors that this particular color space can create. And this is the human eye, what the eye can do. And you want a color space that can maximize this. sRGB does a pretty good job. It dictates where the corners of this triangle are within the color space of what humans perceive, okay? The problem is that sRGB was used partially because it automatically does a nonlinear transfer function. And this is for old school CRTs, right, with a cathode ray tube. And the intensity of the value displayed on the screen was nonlinear. So if you wanted something to be brighter, you used a nonlinear gamma function. There was a gamma curve assigned to it. And this still exists today. Therefore, when you save an image out, it's usually saved in this sRGB format, which assumes that there's going to be some sort of a transfer function. Therefore, the color you see on your screen is not the color stored in the image, and it needs this transfer function to convert it over. This should always be checked, almost always. The only time it shouldn't be checked is when you're dealing with textures that are storing data, right? Because an image texture needs to show up on the screen. Therefore, the sRGB stuff makes sense. But if you're storing data, actual information that is being stored in a texture and then retrieved, but used for some other reason than displaying information, you should uncheck this, turn it off, okay? So 2 examples, HDR, high dynamic ranges, never are stored in this sRGB format because they don't need to be. It doesn't make sense. And then, of course, if you're storing data, it should be unchecked. Then there's the alpha section. This is important, and it's going to be something that really messes you up at the beginning. So if you're having problems with alpha in the class, especially when you start creating your own virtual worlds, send me an email. Don't wrestle with it for 5 hours. If you can't get it to work after 30 minutes, send me an email saying, I can't get this to work. It's not showing up right. So alpha refers to the opacity of the object. How visible is 0 is invisible, 1 is fully opaque. There are 3 different alpha settings inside of Unity. Input texture alpha. If you have an alpha texture, and if you're using a PNG, it'll use what's stored in the alpha channel, that 4th part, RGB, and then A for the alpha. If from grayscale is going to use the average value of the texture. And I tried to give you an example of this here, where I created, these are the textures, the pure textures, completely unlit over here. And these are what show up when you're using the standard shader and this averaging value. So there's no alpha map. Instead, it's taking the data here and it's determining where it should have a cutoff, right? So here, there's nothing going on. You'll notice that this is pure black. However, it's not transparent because the average, there's no average point to work with, right? So it's still 100% visible. Here, though, I've got 50% white, 50% black, and it uses the median point, maybe 0.5, to determine that all the black parts should be removed. Same thing down here. You'll notice that these averages change how things move because I've changed the histogram of each of these images. I've distorted it so that a gradient in between it is smaller or larger. And you'll notice how it affects the fall off of each of these different images and where it impacts. You will sometimes use from grayscale when you don't feel like it, when you don't feel like dealing with it, or maybe you created a mask, right? A cutout object of a face or something and you want to apply it. These are usually called cookies, and they're applied to things like lights. So if I had a flashlight, right, and I was making a video game and it was a horror game, and I wanted to have that, you know, what a flashlight usually has, like kind of several circles and maybe some rays coming out from the side, I could create a grayscale cookie that will have dark values for the parts where the light should be missing, like in these circles and these little areas coming off. And then the transparency will be based upon that kind of information. And then finally, alpha is transparency, messes up a lot of people. What it does is it adjusts the texture so that there is no bleed through when creating bitmaps and filtering. So we're going to get to bitmaps shortly, and this will make a lot more sense. But like I said before, if you have an alpha map, and let's say you have a very tight diamond inside of this, and for some reason, this image gets turned into half the size, maybe 512, and it averages data. On the edges of this triangle, what happens to the alpha value? Does it average it, right? Does it, instead of being pure black on the outside and pure white on the inside, now these become a shade of gray. So now instead of this diamond being crisp, right, you have a halfway color or halfway transparency on it. And the problem gets worse as you continue to downgrade it. Turning alpha is transparency on, when it uses its algorithms to convert that over into different versions of the texture, it will make sure that it does not accidentally bleed those values across the surface. It will treat the transparency, it will look at the transparency and say, this is the way it should be. I'm not going to average or blend things together. The name does not explain that at all. You really have to look that one up. I've seen, even I have gotten it wrong for a long time. So be careful with that one. Okay, wrapping. This is an example we'll do. But the idea is, I mentioned this already with the road, but here, what happens when you exceed the 0, 0, 1, 1 space? And by the way, yes, your values can be negative or positive. It doesn't matter. You have 5 different options. There's repeat, which as I showed with the road would just repeat. So this one is repeat over here. This is a flat plane that I created. And what I did is, this is the normal 0 to 1 UV space, this red part, but I took the UVs and I scaled them up 3 times. So now they cover not just one coordinate system, but they actually go from 0, 1 to 2, 2 up here and -1, -1 down here. So we have 3 of these going in each direction, right? So repeat just repeats the texture, right? So here, bottom, 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 left, 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 always on the left side of each repetition. Then we have clamp. Clamp is going to take whatever the edge value is of that image, and it's going to just spread it out all the way to the edge of the object. It clamps it to that value and it doesn't change. Mirror, as I mentioned before, inverts it. So in this case down here, this is mirror, and what you'll notice is that when it crosses over, you have a mirror image exactly on the other side, like if you held a mirror up to that part and it reflected over to the other part. Mirroring is nice because it automatically makes the texture tileable. It will use the same values on the edge on one side for the other side, so it looks kind of seamless. It's the really poor version of seamless when you don't know what you're doing, because very quickly tiles will repeat and you'll see the art, you'll see that it's a mirror over and over and over again. Then there's mirror once, which will do it once and then clamp the object. As you can see over here, it does one set of mirroring, and then as soon as it goes off of that, it clamps things down. And then finally, you have per axis. And what that means is you can specify a wrap mode for one axis and then a different wrap mode for the other axis. So here we have clamp on the vertical, and then on the horizontal, we simply have a tile. So this is where we get into minification now. As I mentioned before, if you have a terrain, an entire terrain with one texture, right? It's got all kinds of crazy details and things going on, and you zoom way out so that the entire terrain is in one texture or one pixel, what do you render? That's a lot of information, a lot of color values. How do you determine what this entire pixel should be? Because you're not going to evaluate every single bit of the terrain, right? That doesn't make sense. Worse off is, if you think about it, is if you're really, really far away, right? And you've got this terrain. What happens? Let's say you're sampling right here in the middle, right? And this terrain is a park that turns into a city, right? It's like in New York City, right? Here are skyscrapers over here, and here's woods and forest, right? This is green, and this is very gray. You shift that camera over the smallest amount, way far away, right? Just a tiny little bit. And what happens is that pixel right there will move all the way over to this. And all of a sudden, a pixel that was gray will now appear completely green. And if you move over a little bit further, let's say the city's right here, you move over just a tiny inch, it goes back to gray over here. And you get this horrible shimmering effect where the pixel values keep seemingly randomly changing. They're not, they're sampling the scene, but it's not taking everything into consideration. It's just taking a single point into consideration. So what do we do? Well, to deal with this problem, and it's actually a 2-part problem. There's also magnification, which is what do you do when a texture gets big? But for those, you just interpolate, right? You just say, oh, well, if a texture gets too big, I'll just use the nearest neighbors and I'll figure out a value. Minification is a little bit more interesting. You can also use nearest neighbor, where you use all the textures around it. So if we were sampling that one point, we could keep growing this bigger and bigger and bigger and use larger samples of textures. However, you've gone from accessing one texture to now accessing 4 to 8 to 16 to crazy numbers of accessing. That's not good. Instead, what mipmaps do is it pre-calculates those averages, right? Because technically, if you're at 1 pixel and you decide to go out to the nearest pixels, right, the 9 by 9 after that, or the larger one after that, well, you could pre-calculate all those. And that's what a bitmap does. So if we, let's see, clear this out. Here's an example of the old way we used to do bitmaps. Now they're auto-generated by the engine for the most part. But in the old days, or even today, if you want to make sure that the bitmap looks a certain way, you can generate them yourselves using an NVIDIA Photoshop plugin. So this is the original texture here. And what it does is it takes them down by powers of 2. So say this was 512, 256, 128, 64, and so forth, all the way down. And it goes all the way down to 2 by 2 or 1 by 1. It depends upon who you ask. Unity says one thing, developers say another. But it'll take all these different versions, and when it's sampling a texture on a surface, it'll see how far away you are and determine which one of these to use instead. These already have that averaging, that multiple sampling encoded with them. So you don't need to do 100 samples. You just need to pick the right bitmap. Bitmaps stand for multum in parvo, many things in a small place, and they are automatically calculated for you inside of Unity. However, there are some caveats. One is the fact that it does increase memory usage. If every single texture in your scene has a bitmap, you've just increased your memory usage by 33%. So if you're trying to optimize for a mobile device or or if you're hitting your max cap, you might need to turn off bitmap generation for certain things. In addition, because bitmap is a depth problem, what do you sample when something is a certain distance away? Some textures should have it disabled. For instance, UI textures or skyboxes, which are basically, if you think about it as a semicircle or a half sphere, usually, or sometimes a full sphere, but they are rendered from a certain distance away always. So the first thing that happens is it will render, a skybox will usually be like clouds in the sky, okay? It'll render this first because clouds are so far away. The idea is you as a human being moving around on a surface, you never get closer or further away from the clouds, right? The scale that you move at is so small compared to the scale of clouds in the sky that this can get rendered first. It doesn't matter. And distance never changes. It's like the sun. The sun's so far away, it doesn't matter where you walk on the earth. It always looks like the same size. The next setting we want to talk about that is super important, and I even got wrong for a very important demo once because I completely forgot about it, is the anisotropic setting. This setting allows you to increase the vertical. Notice I said vertical samples on a pixel. So if this was a single pixel, normally you'd sample once, right? What this allows you to do is do 2 samples or 4 vertical samples or 6 or 8 or however many samples. But the idea is that for surfaces like this floor that are perpendicular to the camera and at a glancing angle, what you'll notice is that as you go further off into the distance, you get this nasty blurry crap going on. It looks like junk. This increases number of samples vertically, and as you do so, you'll notice that the floor begins to look better and better and better. In fact, I left this off on a particular project, the Warsaw one, and I got a lot of crap for it because they said it looked like weird, blurry carpeting in the background. And as soon as I fixed that and turned it off, things looked a lot more like the wood that they're actually supposed to be. So anyway, the problem with anisotropic sampling is that it does increase how many samples you take per pixel. Luckily, most of the stuff is hardware supported and it doesn't really incur much of a penalty, but on certain devices, especially mobile ones, it will hurt performance. So a lot of times you will want to keep this very low, if on at all. Okay, so now we get to do some actual coding. So let's talk a little bit about this. First thing to understand is that since we're working with textures, as I mentioned before, you need UV coordinates. So either your model that you're using had them embedded into it inside of the 3D modeling application like Blender or Maya, which is the usual thing, or in the case of everyone in this class for the moment, you need to add additional UV coordinates to each vertex. The good news is it's the same stuff you've already been doing. You're just going to create a new list vector2, UVs equals new list vector2. You're going to add those vectors to that object and for each vertex. So the idea is we'd have 3 vertices in this case. And then you're going to use mesh.setUVs to add to that object. Great. So yeah, create a list, store them away, add them to it, and then stick them into the mesh using setUVs. Now, the important thing to understand about this method here is you'll notice that it has a 0 at the beginning. The other ones didn't dictate where you stick the UVs. This one does. The reason for that is because you have multiple UV slots. Why would you do this? Because you can do some really interesting effects with it. So for instance, in TextCord 1, there's a whole separate UV system, sometimes auto-generated by Unity, that lays out all the objects so they're unique across the surface, and it renders light baking information onto them inside the game engine. So this first one are your colors that you set for the surface, but this second set is used by Unity to determine how to light the object through pre-baked lighting. Why would you pre-bake lighting? Because you can spend hours or days generating incredibly realistic lighting inside of a scene that you could never do in real time. And you can then use them inside of here. So what you're doing is you're trading off memory. It takes memory to store this stuff, but now you don't have to do any real-time calculations. Other reasons is, if you notice the type is a float 4. You can store whatever you want in this texture coordinate. I call it a texture coordinate. The semantics call it a texture coordinate. But as I mentioned before, semantics are kind of the original idea intended for it. You don't have to use it for texture coordinates. You can store whatever data you want to inside of these so long as it's floating type. So if you need to use it for something completely different or a whole other purpose, go for it. Next thing you have to do is you need to then render your object. So after you've done that, you will then have your object rendered out. You will need to apply a material to it, and then you'll need to put your texture onto that object as well. So here you'll see a triangle. The most common issue you're going to run into, just like winding order on your vertices, it will be backwards or flipped in some way. So always render it and assign to it a material or a texture like this one that has writing on it. That's going to be the fastest way for us as human beings to identify that things are wrong. If you use a texture that's meant to be tiled or that doesn't have a lot of interesting variation, you may never notice that you actually assigned it backwards until it's too late. So I always recommend having a test texture like the one that I've created here that you apply to the surface to make sure things are showing up properly. Then are the shaders. So now we need to add the ability to work with this texture object. And to do that, we need to add two things to it. The first thing is we need a slot in our material. And if you remember from hopefully both the quiz, the lectures, and me going over it over and over again, is that you have a properties section, okay? And the properties section was blank for now, but you are going to create a property to hold a texture, and then you're going to assign it to that slot that you have created here, all right? So here, we'll be creating our first property. We'll be calling it main text. This actually means something inside of Unity, and I did write about it in the previous lecture, but most likely everyone completely ignored it. But this main text means it's the main texture that Unity can use. And Unity has a lot of built-in shaders. For instance, in Unity, when you select an object, did you ever notice that you have an orange outline? You didn't code that. You didn't make that. It's inferring what to draw. It has its own set of shaders on top of the ones you're working with that get drawn to the surface. Having main text as this name tells Unity that this is the main texture it's working with. So it knows how to properly integrate it within its own pipeline for the editor. There's another attribute you can use called main text as well when you want to name this something different. Like main text to me doesn't make a lot of sense when I actually want to call it albedo, because albedo means pure color of an object with no lighting. So I could name it _albedo and then use this attribute instead to tell Unity, hey, this is the main texture in case you need it for some reason. You specify the string, which is the nice name in the inspector, and then you specify the type, which might be float or range if you want a slider. In this case, it's 2D. If you're working with 3D textures, it would be 3D instead. Then you specify the default type, white, black, red are options, or normal. In our case, we'll just specify white. And then you have to add these annoying curly brackets on the end that I always forget, which usually causes an error. So if I screw something up in the example today, that's probably it. And then remember that I mentioned, but you probably forgot, a property that is defined, or I should say declared, does not mean it is declared in your shader. This is the glue that links Unity to your shader. It is what shows up in the inspector. It does not mean you have actually created a variable in your shader code. So whatever name you give this here, you need to make sure you also create a variable in the shader snippet that corresponds to it. Same exact name. So please, if you can't cram something into your head anymore this lecture, the one thing that you are probably going to mess up on a homework assignment is not redeclaring this variable within the shader code and making sure that the names match. That is what you will mess up. Also, the types need to match. This is 2D. This is sampler 2D. They just made the name a little bit shorter, but that's what you need to do as well. And you'll, of course, have a texture slot now showing up in your inspector, and everything should be great. And you will also have declared it in your shader, so you can use this variable within the shader as well. Okay, the next thing we need to do is update our struct, right? So our struct before was using the position semantic and possibly the color semantic if you had implemented that, definitely if you were a graduate student. We now need to add the text chord 0 semantic to it. Give it a name and a type. Texture coordinates can be 2, 3, or 4-dimensional. In fact, most likely by default, it will always be 4-dimensional. You just might not choose to use the other slots. Once again, in order to keep memory in nice, clean slots inside the GPU, almost every variable you declare, even when they're not size 4, will always be size 4. You just don't use those variables, okay? That's just how it works. So in reality, this is a float 4, and the other values usually just get defaulted to 0. I'll say this for the 2 people in the class who know what I'm talking about in the future. You have an X, Y, a Z, and a W coordinate. X, Y, Z by default are set to zeros, so 0, 0, 0. However, the W coordinate is almost always set to 1 by default. This has to do with something called homogeneous coordinates or projective geometry. Don't worry about it if you don't understand it. But do know that X, Y, Z are 0. W, the 4th component, is almost always set to 1, in case you're wondering. To query a texture, it's really easy. They give you the method or function called text2d. You specify the name of the texture, which was underscore main text. That's the one you had specified before. And then you specify the coordinates. It's a single variable in this case, the idea being that you would pass it a float 2, right? A 2-element float, the X and the Y coordinate, or whatever you want to really of it. You specify that in there, and it will then return to you a value. Usually, because this is color information, you store that in what's called a fixed 4. If you recall from the last lecture, I talked about how you have different precisions. A fixed 4 is usually between, I think it's something like 0 and +2, or maybe -2 and +2. But the idea is that it's a smaller range of data that's meant specifically to handle color. If the texture that you're working with is actually data, not color information, you're probably going to want to store that inside of a float 4 instead, the RGB and A information, so that you have full precision. You're not losing anything when you're working with it. If you want to know more, there's similar documentation on the HLSL language, as well as the CG language on the NVIDIA's website in Microsoft for HLSL, and it has 1D and 3D functions. Of course, it's text 2D or text 1D instead of 3D and so forth. Now, once you've sampled it and it returns to a value, you can do whatever you want to with that value, right? It's your time to either manipulate it or just return it. So here we showed you making that struct. Here we're showing you that we need to go to our vertex shader. Since we're using structs this time, and the struct contains a semantic within it, we only need to, well, pretty much nothing needs to change here. It's the same input here, same output as before. The only difference here is that the output needs to, we need to transfer the input UV chord 0 over to the output UV chord 0. Remember that you defined UV coordinates for the 3 points. You are now passing this off to the rasterizer, which is going to convert this over into a series of fragments or pixels, and each of these is going to get an interpolated value between the value you specified here and here. That's why it's important to pass that on, so that every single pixel or fragment gets an interpolated value between each of these, okay? So it might seem like, why am I bothering to do this? Well, there's a very good reason. So the rasterizer can tear that thing apart into tiny, tiny, tiny fragments and provide each one with a proper value. And then the pixel shader will then operate on each one of them. The pixel shader is where you do texture accessing. I believe in the latest shader model, as well as in some other cases, you can at times access the texture inside of there, but it's usually not, and it's almost never supported in older hardware, especially shader model, I think 5 and before. But you can, if you want to, in later versions. For the most part, you will be doing text 2D inside of the pixel shader only. So if you find yourself trying to do this in the vertex shader, you're wrong. Don't do that. Stop it. That's your problem. So once again, we have our input coming in from here. So our output now becomes our input. and we've targeted using SV target in this case. You could have also optionally used color for the old DirectX 9 if you remember from the last lecture. We would then grab our value, passing in our XY coordinates here from their UV. And then in this case, we simply return the value, but you could do whatever you want to the value. You can manipulate it however you want to. You could sample multiple different locations if you wanted to and return a different value. That's the part where you get to mess around. All right. So the last thing I want to mention is time. And actually, before we do that, let's go ahead and jump into Unity really quick. No, I do not. I guess I will keep it, whatever. Let's go ahead and jump into Unity. I'm going to create a new scene really fast. And what I would like to do is I'm actually going to open up. If you want to follow along, feel free to, or don't. That's why recorded lectures are so great, I'm told. And we're going to use the same triangle script that we've been dealing with in the last several lectures. And we're going to update this to have UV attributes. So you can see that actually in real time. And hopefully I make some mistakes. And if I do, you get to see how to combat them. So let's see, let's get rid of this and let's go to our triangle example. And I'm going to delete just a little bit of code I had added so that it looks the same as something that you would have created as well. Great, that's perfect. Okay, so our triangle mesh from before. So all we need to do now is we need to add a list. And this time we're going to do vector 2 because we're only dealing with two-dimensional coordinates, but you could optionally do vector 3s if you wanted to. I will be doing vector 2s, and let's just call this UVs equals a new list of type vector 2, right? And we'll move on now. So now we have our list. All we need to do is populate that list. So coming down here, we'll do UVs.add, and now we need to take a look at our vertices and figure out how we want to do this. And what I usually like to do is to try to draw some sort of a picture. So this is at 0, 0, 0, right? 1, 1, 0, and then 1, 0, 0. So we're starting off, what's the fastest way? Let's just use Paint so we don't have to wait for Photoshop to load, right? So here we go. We've got 0, 0, 0 here. Then we go over, up 1 and then over 1. So 1, 1 over here. And then we do 1 over and then 0 over here. And then, of course, the idea is that we would hopefully have a triangle. That is annoying functionality. Is that really how Paint works? I guess so. So there we go. So we have our triangle. And we have specified it to be 0, 1, 2. So it's going to be, let's go to this. It is going to be 0, and then 1, and then 2. And this is clockwise. So everything should render appropriately. And now if we want this to sample our texture, we can sample it however we want to. Let's do this easy. So I'm going to assume this is my texture right here, kind of superimposed on top of it. Our texture's coordinates are 0, 0 down here and 1, 1 up here. So I'm going to want this one to be 0, 0. I'm going to want this one to be 1, 1. And now this one is also just going to be 1 unit in the X and 0 over here. There's nothing saying I have to sample it like this, but this is just an example. I could have picked a smaller region over here or wherever I want to. It's entirely up to you and however you decide to create your object. If you were creating a quad, for instance, you would have another point up here, and this one would be 0, 1 instead. So coming back over here, let's go ahead and add our 3 UVs. So we said the first one was going to be 0, 0, 0. And we can go ahead and save that. And I'm going to copy that and paste that twice. And I need to add an actual vector 2. So we're going to do a new vector 2. And then within that, 0, 0, 0. There we are. I'm going to copy that line. And let's see, new vector 2. Oh, yeah. Sorry, George. Too many parameters. Grab that. Paste that here because we're lazy. And now we'll do this one. Well, this one needed to be 1, 1. So we'll do 1 and a 1. And the last one needed to be 1, 0. Lines up very nicely with what we're doing. Okay, now we have our indices. Well, this list is set, this list is set, this list is set. They're all the same size. We should be fine unless we mess something up with the winding order or this part as well. And that can happen. And then, of course, our indices get set. Our mesh gets made. We set our vertices, we set our indices, and then we're going to set our mesh.set UVs. Once again, we take a look at the different ways we can pass in information. First is our channel. We want to always, the first channel is almost always what you want to work with. Almost every shader inside of Unity that's already been built is going to use 0 as your general UV coordinates for coloring the object. 1 is going to be used for light baking, so you usually don't want to mess with that. And then next up, we just specify our list. If we scroll through the different types, we'll notice that, okay, there's a bunch of different ones. You can take in vector 2s, 3s, or 4-dimensional ones. Okay, that's all interesting, but what we want is a list. So we can choose UVs. and semicolon after that. And with that, we've added the attribute data that we need. We're good to go. If we come over to our Unity world and we go over here and we wait for Unity to hopefully actually work, there we are. We can right click, create empty, and let's call this triangle. Go ahead, go to add component, add our triangle script. We need to put a material on this, so why don't we go ahead and just create something. So let's just call this triangle and go ahead and attach that to our triangle mesh renderer here. We click on triangle. We have the standard shader being used. Should be fine. I don't see any reason why not to. But if we really just want to test with no lighting calculations, click on standard, go to unlit, and let's choose texture instead, right? Or actually, right now, we might want to just choose color or something like that because we haven't yet assigned a texture to it. It's up to us. If we go ahead and hit run, let's just see, there's our triangle. We don't have any texture information yet embedded on it. We don't have a shader that can react to it. So for right now, it's just going to render out whatever's going on there. Now let's go ahead and create our shader, right? So I'm going to go ahead and work with the shader we had done last time. So let me find that really fast. So I believe it was, we'll do minimal shaders alt in this case. That was an alternate version with a slightly different way of passing data around, to give you an example. First thing I said we need to do is, well, first thing we want to do is go to that material, right? And let's see, let's go under scripts, triangle, and we're going to change our shader to be hopefully your name if you had stuck with the convention. And then we're going to do minimal shaders alt. This particular shader I had written to cover the graduate student example to make sure it actually works before I assign something to you. So it does have vertex color information. So that's why you're seeing those different colors there. If you watch the video I put up there on the subject, it's the exact same code for attributes of colors. And I believe I even supported normals on that one at some point. So going back to the triangle, we have our mesh and our material object right here. It has no properties or parameters for us to work with. So coming over here, we need to do that. So in our brains, we need to try to remember the Unity Shader Lab format for this. Everything begins with an underscore. This is going to be the variable name that we have to declare later on. So let's just call this albedo texture, or if we want to conform to Unity standards, we'll call this main text. It's entirely up to us. We then put what are these parentheses around it. And then the first part is going to be the, let me turn insert off so it doesn't undo everything. We then need to give it a nice name. So we'll do albedo text. And then we need to give it the type, which is 2D for a texture that's two-dimensional. Then we need to specify the default type, which is going to be white. And almost always, the part that I always screw up is putting the curly braces on the end of it. Make sure you have that. Okay, so we got our main text defined as a property. We come back over to Unity. Even though we're running, it will actually recompile the shader and update it in real time, which is actually a giant save on Unity's part. That's nice that it can actually hot swap the shaders in real time. Although it might screw things up. I have had issues where I've had to restart Unity when I've made large changes to the textures or other objects due to the artifacts not updating when I was making changes. So do be aware that sometimes a restart is the best thing for you to do. Now we need some sort of a texture. So let's go to right click. I'm going to go to import a new asset. And let's see, we've got a bunch of different assets. Let's choose you choose whatever you want to. I'm going to use my Demigorgon texture here. And let's go to triangle. And once again, select the material. And I'm going to grab the Demigorgon and throw it into that texture slot. Now, once again, nothing shows up. Why is nothing showing up? Because we don't do anything in the shader with it. We're supplying data, but it doesn't know how to use it yet. We haven't even set up our semantics yet either. So those are all reasons why stuff isn't showing up yet. So understand that as you slowly start putting these pieces together, you're not going to get results until you've finally written that shader code. You can set it up and have it all showing here, but nothing is actually going to reveal itself yet. All right, so we've got our properties, our main text. The first thing we're going to do before we forget anything is grab that variable name, copy it, and we need to create the variable in our shader code snippet right here. How do we do that? Well, we're going to come in here and we're just going to create what's called a sampler 2D. This is a specific variable type for HLSL, GLSL, and CG. It samples a two-dimensional texture. It does a lot of work for us, so don't worry about it. Just burn that into your brain. Sampler 2D. Same name as before, put a semicolon. Now we actually have that variable existing. The other thing to do is when you're writing shaders and you're slowly adding things that you're learning for the first time, jump back over to Unity and you'll notice it updated really quickly. Check the console for errors. If you add 40 lines of code, I guarantee you'll probably end up with like 20 different errors. Jumping back and forth and letting it upload will at least warn you that whatever you just did is what's screwing everything up, and you won't have to. Debugging shaders is harder than debugging most of anything else. Okay. So give yourself a little bit of room and do it step by step sequentially. It will save you and keep your mind sane. Believe me, I've gone crazy from some of the errors in these shaders. So,
Ooh, quick question,
now,
George, on that note.
yes.
Is there a debug.log equivalent in shaders?
No.
That's what I thought.
There are debugging mechanisms, and there's the profiler and a few other things you do, but shaders run on the GPU, which is a completely separate piece of hardware on your system. So what can you output? Well, sometimes you can output errors or warnings, which is what shows up in the console. However, the best way that I typically debug information is I convert things into colors. So I'll make different ranges or different values using if statements, different things. So for instance, in my shader, if my math was wrong, I might do some sort of a statement like if my value is less than 0.0, maybe I'm doing something with dot products or something. I would then have the color come out to be, like a green value instead. So I would do like a fix for RGB, something like that, alpha 1. And then I would create different ranges for the different values that I expect to come out. So in many ways, it's kind of fun because you're now converting code into a completely visual mechanism, and your whole scene then comes alive with different colors. You could take the UV coordinates, for instance, and map them to RGB colors, right? UVW could just be RGB instead, and the values you supply could then become colors on the surface to see whether or not your UVs are properly set up on your object. So that's typically how you debug shaders, is you convert things into visualizations for you to test in real time. It takes some getting used to, and it kind of sucks at first, but it's kind of fun after a while, because in many ways it's like, what is that? It's called synesthesia, I believe, where you can see like what you hear or what you smell or taste, and you're kind of doing that in a computer. You're converting these datas and values into visuals that you can then interpret.
Yeah, cool. That sounds good to me. Thank you.
Okay, yeah, no problem. So here we already have an error, right? So always jump back and forth, and that's because I'm using values that simply don't exist. So let's go ahead and get rid of that nonsense really quick and come back to here. So where we left off was we need to update our struct, right? So right now we have in the example in the lecture, I showed you how to do it with two structs. In this example, let's do it without two structs. Let's do it instead using the parameter list and binding those semantically. So in this case, we will do a, what was it? We want a float. And then once again, we can do a float 4 or 2. Like I said, it doesn't really matter. It's going to be any of those. Well, let's just call this UVs. And then we will bind this to text chord 0. Apologize if you hear a child screaming in the background. It's bedtime and they're giving my wife a hard time. So UVs text chord 0, it's binding that. So the input from our shader that we bound to text chord 0, slot 0, is going to now be bound to this variable. We then need to push this out to the fragment shader. So over here, we'll do an O output dot, and now we need to update our struct output, right? So we can once again do a float 4, and then we can just call this UVs as well. Usually you want to give it a number because you'll have multiples. So maybe I'll call this UVs 0. And let's do, really UV, because plural doesn't make sense because it's assessing one particular UV. So let's change that to just UV0. Let's see. So UV0, that works. So then we want UV0 to also be bound to the output, which is also going to be text chord 0. Now, the input is going to be UV0. Output.UV0 is going to be equal to input.UV0. All right. It is a little confusing to name them the same thing. just like in C# code where I used the same name but used this pointer. However, after doing it for years, trying to come up with different names for the same thing really stinks. And if you come up with a convention, you can always rely on the variable names being correct. If I always use UV0, 1, 2, 3, 4, everywhere, I never have to look back into other code or potentially other shader files to make sure I didn't name it something different with a capital U or some other weirdness like that. Remember, the variable name is I or 0, I for input, O for output. That's what matters. Okay, so that being said, we have now transferred that data over here. The vertex shader will transfer that UV out. It will then get rasterized and split up into multiple UVs that are interpolated over the entire surface. And then our fragment shader is going to pick that data up, and now we need to operate on it. To do that, we need to, of course, grab the value and do something with it. So let's store this to a temporary value. We'll do a fixed 4 because we don't need a lot of space. We'll store it in temp. And then once again, we're going to use the text2d function. And then what we want to do inside of text2d is provide the UV coordinate, or excuse me, the texture first, which is going to be main text. That's what we named up here as the property and our sampler 2D. And then after that, we are then going to want to provide the UV coordinate. That is going to come from I, our input variable, which is the vertex2 fragment struct that we created up here. And then we want to access .uv0, .uv0, okay? Now, uv0 is a float 4. What we want to do is specify just a two-dimensional lookup. So I'm going to specify .xy or .rg or .uv. All of those mean the same thing, but shader languages support those different ways of indexing into that vector so that you can, to make it easy on you, right? Because when you're dealing with, you know, this is a texture coordinate now, right? As opposed to XY, where you might confuse it with something else, or RG, where you might confuse it with a color. UV very much means texture coordinates, so I don't get it confused with all the other things that I'm doing in my program. Okay, we access temp, and now all we need to do is spit out temp. So let's make the color, which is our output, right? Out fixed for color here, SV target is going to take our texture value, whatever we get, and send it to the screen to be displayed. Let's come back here. Now we've got an error. It says undeclared identifier I at line 31 on DirectX, Direct3D, DirectX 11 is what that says. So double click it, come back here, and what we'll see here is that we don't have an input struct. I forgot that I was using, what are these? Just variables. So instead, what we want to do here is just grab our variable name, UV0, or just get rid of the I. That works too. Now come back here, let it go, and let's see. Texture 2D, no matching 2D intrinsic parameter matches this particular thing. Most likely what I've done is I capitalized the D. So let's uncapitalize that and come back here. And now it says invalid subscript. See, this is why I say it's a process. Invalid subscript UV at line 37, double click, take a look here. It's saying that I can't use UV. I'm almost positive you're allowed to. I don't know why. Or maybe it's ST for, let's try ST. Yep. Okay. Sorry. HLSL uses ST. It's GLSL, I believe, that allows you to use UV. You can use XY or RG. They'll all work as well. Identifier, undeclared identifier, texture 2D at line 37. Is it capital? I can never remember. I always screw this part up. No, it's not. So here we go. We have main text, which comes in, which is sampler. Then we have I.uv.st, which is a texture coordinate. So whenever I screw stuff up like this is when I start saying, okay, what did I mess up? Let's start looking at my notes. So coming over here, let's take a look at our, here we go. So here we have texture 2D, it is capital. I had it right the first time and I confused myself. And then we have our UV coordinates and then we specify our X and our Y coordinate right there. So let's go back and see if that's the issue. Coming back around here. So once again, capital is correct. So coming back to Unity and doing a clear. Now, if you clear it out, it'll seem like it's gone. But what you want to do is first, I'm going to pause this for a second. I'll hit run again just to reset things. And what we're going to do is go over to our triangle, and then we can select our shader again if we can't find it, and we can click compile and show code, in which case it'll show us everything and it will recompile the code for the particular object. Now, normally when I click recompile, it also tells me when I have an error. And for some reason, it's not now. So thank you, Unity, for proving me wrong in front of the class again. Thank you very much. I'm going to go back to the shader. Minimal shader alt is the one we were working with. So let's open that back up again. And there's the errors right there. So undeclared identifier I. Okay, let's go check that one out. So we have undeclared identifier I. So here is I right here, and I don't see an I here. And then we have an undeclared identifier value. Okay, well, this is all very interesting, actually. So what is going on here? Because we don't have an I as a variable. So let's do a control F, I. And the only I we have is down here in the V2F I coming in as input from the other vertex stage and setting up right there, which makes me believe that this is actually compiling with an older version of the shader, and it has not updated properly. And I've been having this issue actually today, and I'm wondering if it has something to do with my system. So let us do this really fast just to make sure. I'm going to go to File, Save As, and I'm going to save this as Alt-1, Enter, come back over here. We now have another variant of Alt. And what we will notice is that we do get some different stuff, which is great because I wanted to see something different than the nonsense we were just getting. Coming back here. Now the issue is that we need to give it a different name. Otherwise, we're not going to be able to select it. So coming back over here, minimal shaders. Here we go. And it's not showing up because we still have an error. So let's go over to Alt-1. Texture 2D, no matching parameter. And this is usually because I screw something up in terms of what I pass in. So it says we only can take in a float 2 half, minimum float 2. So it's saying that I can only take in a sampler 2D, which is what we provided it, right? And then it's saying that we can only specify a sampler 2D with these particular values coming in. So we have I, which is our input, right? Which is a vertex 2 fragment, which is here. And then we have our UV0, which is right here. So I.UV0. We specify this as a float 4, and that's assigned to text chord 0. And we specified these two. Let's just use XY for some reason. And no matching 2 parameters. Once again, text 2D. Why are you giving me a problem, sir? Oh, well, one, I'm working in the wrong shader again. That's always fun. So now that I have 2 variants, it's giving me all kinds of chaos. So here we go. I.UV. Let us close you, sir. We don't want you. And we have main text. Let's just make sure I name this right. Main text, main text, main text is that. Texture 2D is this. This returns this value, I.UV XY. And why are you giving me? That's that. This gets here, float 4 comes out of that. That should be fine. You know what? I tried all this before and I know it works. I don't know why it's giving me crap. Let's hit run. There's our shader. Oh my word, George. Okay, you know what? We're going to do this. We're going to hijack this. We're going to force this. So when something doesn't work, you force it to work. So we're going to do a constructor of type float 2, and we're going to pass in these 2 values, right? So this is going to pass, it's going to create a new float 2 type using the X and Y parameter. And it's still giving me crap. Why are you doing this? Well, this is always a fun lecture, isn't it? And this is the hell that sometimes can be writing shaders. Float 2, half 2, min 10 float. Yes, I've provided a float 2. I provided a sample 2D. The only issue that could be coming out of it is that I've actually got the type wrong. So let's see. Yeah, I did all this already. Of course. So we have a color output coming out here. This is the SV target. We have it out here. Let's do a float 2 here. This is the fun of shaders, isn't it? This is
At some point, do you have to do an O.albedo or something?
No, those are for surface shaders.
To actually
All
apply
that
the
stuff has
RGBs?
nothing to do with what we're doing yet. We're not going to touch surface shaders until a few more weeks. That is a confusing topic
All
in
right, my bad.
itself.
Gotcha.
Out v2f, we have this as a float 2 coming in. Then we have a, what do we have as the output? We also have a float 2 as the output for uv0. uv0 gets set to output of uv0, which is a float 2 here. And then down here, we have the input, which is our vertex to fragment input, going into our float. So our main text here, so I'm wondering if what I screwed up is, this is a text 2D. This is within a CG program. I'm going to actually move this down. Now, this should not matter in theory. I'm going to move this below that. And I'm going to hit this. Yes, I know it has 0 parameters. No, duh. And we are going to grab I. This is where I wish it had autocomplete, because then 9 times out of 10 you wouldn't have errors. UV0, which is a floating type 2. Come here. What is this one? Yeah.
Hey, Georgia, this one's a question, not a suggestion.
Sure.
At what point would you ever return something
Check
inside
that
of a
out.
vertex or a fragment shader?
Check that out.
Oh.
I didn't do anything wrong.
All right.
Once again, I'll answer your question in 1 second. This is why working with shaders can be hell. And as I recommended before, jumping back and forth is good. The other shader was producing the error, that alt one that I created before, which for some reason, I don't know why, was still impacting alt shader 1. Might have something to do with the fact that I am hot swapping. Hot swapping, it's an Android term, actually. It's used in other ones as well, but it's used a lot in Android. It's swapping the shader out on the GPU live while the application is running, and that's really not a good thing to do. So I should have been stopping it and starting it. But now you know what happens when it happens to you. So if you try to hot swap stuff, turn it off, okay? And don't do that, because the 2 different shaders, because I had 2 variations of the same thing, were getting confused. As soon as I went back to the first shader and got rid of the ST part, which isn't correct, it works just fine. What you'll notice though is, as I said before, like RG, that's fine, and all that other stuff, that's okay. The issue was between the 2. So now you'll see, once again, code is pretty much exactly what I had. Text 2D, the texture, and then once again, just accessing the different values, RG, or this could have been XY, save, come back over here, and still works. Once again, I am interested in seeing if UV should damn well be supported. I'm pretty sure. We'll do UV on you, and we'll also do UV.UV on you and see if that works. No, HLSL does not support using UV. That is something I didn't know. So we all learned something tonight. So just stick to RGB or XY, or yeah, don't use UV. That is a detriment to the language, I'll tell you right now. Okay, so now what you see is we finally got it working. Texture is mapped to the surface just fine. Alex, what was your question again, really quick, or comment?
Oh, so I was looking at one of the I think it was the standard unlit shaders, which has components for a vertex and a fragment shader. So my question was, at what point would you ever return something from the vertex or the fragment shader? Specifically using the
you don't
term
return anything
return.
unless you bind it to a semantic, because it won't know what to do with it afterwards. You have to precisely define where those values should be hooked up. Semantics are arrows pointing to what in the pipeline it should be connected to. That's how they work. In other languages, we're learning HLSL and GLSL. Whatever you return from the fragment shader is the pixel value. You don't have semantics in GLSL, which is, I actually like that a lot. I think they're completely unnecessary. But this language happens to use them. Does that make sense?
Gotcha. Yeah, no, that's what it looks like here. It's basically just if the struct declares an output, whether it's a struct or just like a fixed for, that's what it returns.
That's correct. You're either returning a struct, or you are binding return values, outputs to semantics, or the struct was bound to, or the members of the struct were bound to semantics. All those are options. It just depends how you want to do it personally. It's a convention thing. It's nothing else. If you go on the forums, you'll find people arguing all over about it. Okay, the last thing we're going to cover really fast before we're done for tonight is time, because I want to show this because I actually have time in the homework example. I asked you to look it up yourself, but of course, I'm always reluctant to make people do things by themselves, so we're going to show an example. Time is, there are many built-in variables that Unity plugs into your shader automatically, and time happens to be one of them, so you don't have to declare it yourself. It's added already afterwards. And time is a float 4, and it stores a different scaled version of time for each. The time it passes in, by the way, is a continually incrementing value based upon the amount of time since the level loaded. We haven't talked about what level means, and actually, you know what? That should actually be called scene. I don't know why I wrote level, but when the scene loads, that is when the timer starts ticking up. .x is t divided by 20, which is 20. Whatever your time value is, so it's the 20th that. So things are going to be slower to progress. And then there's .y for the normal time, t times 2, and then t times 3 for accelerating and decelerating. The reason why is because you might as well calculate the stuff on the CPU. It's trivial, and send it off to the GPU. And because the GPU is doing so many calculations in parallel, why not remove some of these calculations? There's no reason it needs to do it. Calculate it once on the CPU and pass it off. So you're not calculating it, billions of times on the GPU when you don't need to. There's also underscore sine time and cosine time, which are automatically determined on the CPU and passed over as well. Go ahead and do that. Once again, it just keeps you from having to do sine and cosine transforms. And even though lookup tables are used and it's all burned in the hardware at this point, it's still better to use these ones if they're available to you. Okay, going back to the shader itself. So let's use time. The example for using time that I had crafted is a very simple one. We're going to offset and make the UVs move and animate them, similar to that swirl effect I showed you before. Because time is built in, we do not need to add it to a property, so we don't have to do that. The first example we're going to do is just offsetting the values using time's YY value. Or actually, you know what, that's in the lecture notes. Let's use a different one in person so you get something different. So we're going to do this inside of the vertex shader because that's only 3 points being processed, right? If we did it in the fragment shader, well, the fragment shader is just going to take, the rasterizer is going to take those 3 points and make them into, potentially hundreds, if not thousands of points. Why do the operation thousands of times when we can do it over here first and then have it automatically interpolate across the object? So coming over here, instead of just taking UV and mapping it over to the other one, let's transform this, right? Let's create our own function to manipulate this value, our corresponder function or functions as it were. So we're just going to offset this. So our UV value is going to be equal to UV0, which is a float 4 right here. So UV0 plus time. And what we want to do is I'm going to do time dot, and we need this to be of size 4 as well. You need a 4 size vector needs to be with a 4 size vector when you're doing operations. So time dot, and I said we do it differently, right? We'll do x, y, and then just y. So what this is the time divided by 20 for the first element. Then it's going to be time, and time for the other elements. All right. So save that, come back over here. We get another error. Time is not declared. So coming back over here, we will see that it should be underscore time because everything in Unity, all variables are an underscore. Save that, come back over here, and there we go. And what we'll notice now is that it's animating, or it's offsetting that texture value as our level time moves on. And because we have different rates for one dimension versus the other, you'll notice that it's moving vertically faster than it is moving slowly horizontally. Now, if you wanted to have precise control over each one, what we can do is add parameters to our code, or properties, excuse me, that would control those different rates. So let's do that really fast before class ends. We can do this, and we'll come over here. Let's go over to our minimal shader Alt1 code, come up to the top. We'll add 2 properties. We'll do an underscore X rate, and then we will default value set to 0, and then we'll do an underscore Y rate. Or U and V, you can call it whatever you want to. It's entirely up to you. Actually, maybe we should do that. Keep the conventions. Don't confuse people. U rate, then we need our nice name, and we'll say U rate, U speed, And then we'll do the same thing for the next one in a second, but in the V direction. This is going to be a float value. So we could write float, or we could use range and specify a range. And maybe I'll make the range a -4 to a +4. Okay. And then we'll do this, copy this, paste this, because I'm lazy. We'll do a V here. And then we'll once again, we'll do the range same, -4 to +4. Both values starting at 0, so it shouldn't move. Now, though, once again, we have to declare these variables. And because this is a range, this is a float, we come down here. And I like to keep them together. So under our sampler, we do a float, and then we'll do U rate, and we'll do a float, and we'll do a V rate. Now we need to use these inside of our vertex shader. Once again, do it in the vertex shader, because unless you're doing nonlinear stuff, it's going to linearly interpolate the value for you. So why not do it in the cheaper area, which is the vertex shader, as opposed to the more expensive fragment shader? So to do this, we need to change how this looks, right? And let's see. So we did, is this the wrong shader? Did I have two versions that I see? This is Alt shader, this is Alt 1 shader, and in Alt 1 shader is where I did this. So let's copy this, put this over here, and let's see, let's edit, redo, there we are. Paste this here, so we have the same code on both. Now what we need to do is manipulate the coordinates together. Easiest way to do this is we need to actually create a new floating point value that we're working with. So UV0 is a, what, a float 4, actually it's a, input is a float 2, output is also a float 2 in this one. So let us just do a float 2, and then what we want to do is we're going to take UV0, our input value, dot X, and what I want to add to that is the U rate, right? Or actually multiply that. Let's multiply that, not add, right? So let's do U rate. So actually, I'm sorry. We want to increment this through time, right? So we'll do time and then dot X to modify that one. And then we also want to multiply the time by that rate because it's a speed, right? So we need to multiply a speed by a time variable in order for the units to cancel and for us to get an offset amount. Okay, so that's for our X value. Now we can copy this same thing and paste it, and we need to just change this now to the Y coordinate instead. So instead we could do UV0 dot Y plus time dot, well, if we did time, we want to use the same kind of time, otherwise they're scaled. We'll do the 20th version in this case. And then now instead of the U rate, we will use the V rate instead. Coming back over here. Now, if we come to our triangle, go to the material and check out our shader, we still don't have any properties. So this is still using Alt. So let's change it to Alt 1 really quick. And now what you'll notice is we have two sliders, a U slider and a V slider. And if we move these, what you'll notice is we get different rates for the different directions. So if you were making a stream in your game, you might crank this up to like 4 on one side so the water would flow naturally going down the surface. So for instance, import new asset, I believe we had, I think I deleted it. We had lava at some point, right? But I don't think we have any. So let's just use, GPUs, right? Oh, what are you giving me crap for? It's an import error because I'm actually running the application while I'm doing all this stuff, which is never a good idea. Let's take the GPU and stick it there, okay? And now we've got an endless stream of GPUs being sent to me in my computer. Okay, so that's it that I wanted to cover for tonight. We did very, very incredibly basic stuff. We only accessed it and we made it visible on our screen, and then we made it so we could scroll through it. Your homework assignment is going to go a tiny bit further. I might have you do some fun with twisting it or manipulating the different color values in the fragment shader afterwards to do some interesting effects. Maybe that grayscale thing I had mentioned before, or adding noise to it. We'll see. But either way, that's it for tonight. I can stay on if anyone has any particular questions about anything for a few minutes. Otherwise, thank you all, everyone, and I will see you again next week.